Hello and welcome to today's video. In this video, we are going to discuss integration over intervals that we have not touched so far. You will remember that up to this point, we have always integrated over bounded intervals. So intervals that include both bounds, or at least where there is a bound for both sides. So they do not extend to infinity. And they also do not extend to any points where the integrand, the function in the integral, is problematic in some way. Now, of course, with the definition of integration in place, one can try to do that. One can extend the integration limits and then just see what happens. And this is exactly what we're going to do in this section, which is called improper integrals. Now I'll start with the definition right away. Unfortunately, this definition is a little tedious, a little technical, but you'll find that the process of actually computing these integrals is not at all that complicated. I'll give you a few examples right after the definition that show you how to apply that. The thing is, this definition does become a little tedious because we're talking about convergence of certain functions defined by integrals. That makes things a little technical here. But bear with me until after this definition, and with the examples that we're going to look at together, I think you'll get the hang of it very quickly. So we have different parts to this definition. Again, mostly because of technical stuff here. Let's say we have an interval. Let I be an interval, and we'll first have a look at intervals of the form AB, where A is included, but B is not. And the reason for that is we want to allow for B to be infinity. Or we want to allow for B to be a point where the function, the integrand, is not defined. So we want that to be an interval where B is in R and possibly also infinity, and A is just a real number. And then let F be defined on that interval, be a function with real values. Now, if F can be integrated, so if F is integrable over every interval that is bounded and contained in this A to B, in this interval I. So every interval of the form A to T, with T included, for T in I. Then we can try to move T towards B, so we can take the limit of T towards B, and hope that this limit exists. And if it exists, then we'll define that as the so-called improper integral of F over the interval A to B. So, and if the limit of the integral from A to T f of x dx as t goes to b, and as b is the right boundary of that interval, we have to let t go to b from below. So if that limit exists, then we call this limit the improper integral, and we just denote it by the notation integral from a to b. So b could be infinity, that's something like a to infinity, for example. F of x dx, that is then defined as precisely that limit. So t goes to b from below, integral from a to t, f of x dx, and we call that an improper integral. So that is the improper integral of f over the interval ab. Now, of course, we did that for the right bound of the interval. We can also do this for the left bound of the interval, which then could not be infinity, but maybe minus infinity, or again, some point where the integrand is not defined. So the second part of the definition is pretty much the same as the first part, but now with the left bound. So let I be an interval of the form a to b, where now a is not included. An interval where possibly a is in R and it could be minus infinity. B is a real number. And as before, let f be a function on that interval. Now, if f is integrable over every interval of the form tb, where t is now the left bound for t and I, then we can again let t go to a, this time from above, and if that limit exists, we call it the improper integral. So, and if that limit of t to a, this time from above, of the integral from t to b, f of x dx, if that exists, we call this integral, again denoted by integral from a to b, f of x dx, and defined as precisely this limit here. We call that the improper integral of f over the interval a, b. And finally, last part of this definition, we took care of the left side of the interval, we took care of the right side of the interval. Of course, also both sides could be strange. There could be points where f is not defined, or they could be minus infinity plus infinity. Now that's also a possibility. And if that is the case, let me just split this thing up by an arbitrary point in the middle and apply both of the definitions that we just had separately and say, well, this first integral over the whole interval is defined if both parts exist, and then we just sum up. So formally, let I equals AB be an interval where, again, A could be a real number, but could also be minus infinity. B could be another real number, but could be plus infinity. And further, let f be a function that is defined on I. And now I could also be the whole real line. And we choose some point that we call t star. Let t star be some point in AB such that the two improper integrals let me split this thing up at t star, so the improper integrals from a to t star of f of x dx and from t star to b of f of x dx, such that those two exist. And then, if that is the case, we set this integral from a to b, f of x dx, to be the integral from a to t star, f of x dx, plus the integral from t star to b, f of x dx. And again, call that the improper integral of f over the interval ab. So this is how we formally define these improper integrals. Now, as I said, actually computing these is a lot simpler in many cases than writing down the definition. So let's have a look at an example here. So here's part A. We want to compute the integral from 0 to infinity of e to the minus 2x dx. Remember, e to the minus 2x, that's a function that basically, very basically, looks somehow like this. Right, so we're interested in that area here. And as the graph approaches the x-axis, one could expect this might be a finite area. So this might converge, and we will also say that this improper integral converges in such a case. Now let's see if we can compute that. So what we have to do is we have to take the limit as t goes to infinity of the integral from 0 to t e to the minus 2x dx. Now, of course, we can integrate that expression. So that's the limit as t goes to infinity of, well, the integral of e to the minus 2x. That is basically e to the minus 2x. So if we differentiate that, we get minus 2 e to the minus 2x. So we have to divide by minus 2 to make up for that. So this here is the integral. Now let's evaluate that. We get the limit as t goes to infinity of, let's see, minus 1 over 2 e to the minus 2t minus 1 over 2/3 plus 1 over 2 e to the minus 0. Now e to the minus 0 is 1, of course. And this expression here, as t goes to infinity, this here goes to minus infinity, and that means e to the minus 2t will go to 0. So what we get is minus 1/2 times 0, that's 0. And 1/2 times 1, that's just 1 over 2. So the area, this green area here, that is actually 1 over 2. One more example, part B. One over x squared dx. Let's see if we can also bound that one. Now again, that's the limit as t tends to infinity of the integrals 1 to t 1 over x squared dx. 1 over x squared can be easily integrated, so we get the limit t goes to infinity of the expressions minus 1 over x. Remember, 1 over x squared is x to the minus 2, so that can be integrated easily. And we get minus x to the minus 1. Okay? So if we apply that, we get the limit as t goes to infinity of minus 1 over t plus 1 over 1, so that's 1. And now as t goes to infinity, this expression here goes to 0. And of course 1 just goes to 1. So the result here is, that is 1, obviously. So again, there's a finite area under this infinite curve. Now that concludes our quick introduction into improper integrals. Now, as you might imagine, there's a lot more to say about integrals, but unfortunately, we don't have time to cover those interesting things in this semester anymore. So this concludes our treatment of integrals. Unfortunately, this will be the last video of this lecture series. Or fortunately for you, this will be the last video of this lecture series. There's a lot of things that we could not cover, but fortunately, there is Mathematics 2 in the upcoming semester. And the central theme of Mathematics 2 will basically be the unification of what we did in this semester. So you will remember we started with linear algebra, high-dimensional vector spaces. We talked about functions mappings on these vector spaces that mapped a vector to some other vector, possibly change dimension. And then around Christmas, we started talking about calculus. And in calculus, we didn't talk about vector spaces a lot. We have function spaces mentioned sometimes, but usually all the numbers were just real numbers. All the functions that we had just mapped one real number to another real number. So no functions between vectors anymore. And of course, the next possible level here is, how about talking about functions that take a vector as an input and possibly a vector as an output? Can we do calculus on these functions? Can we define continuity on these? Can we define differentiability on these? What can we learn from their derivatives, whatever these derivatives may be, about how these functions work, how they look? And this is going to be the central topic of Math 2 in the upcoming semester. That's called multivariate analysis, analysis of functions with multiple variables. And of course, there's a lot of use cases for these things. We'll also go a little deeper into linear algebra. We'll introduce some topics that we didn't cover in this semester and that will be useful when we talk about multivariate analysis. We'll also quickly cover differential equations, also in a multivariate setting, more or less, or in a multidimensional setting at least, and see a lot of connections between linear algebra and calculus, the two topics that were more or less treated independently this semester. So they are deeply connected, and much of that connection will be more visible in the upcoming semester. So if you'd like to join me on that exciting and challenging journey, I'd be delighted if you would also join me in Mathematics 2. You're of course highly welcome to do so. And as usual, I hope I'll see you then.